Good afternoon, everyone. So I'm Huang, and I'm working with Professor Jonathan Mackler. Today, I want to talk about tomography reconstruction of wind velocity profiles in atmosphere. First, I'll give a brief introduction about why we are interested in such kind of reconstruction, and then I will talk briefly about some background knowledge as for what instruments we use in order to get information from the atmosphere, since they are so high away from us. After that, I will mostly focus on the tomography reconstruction of the wind profile. So firstly, since our goal here is to reconstruct the wind or temperature profiles in the atmosphere, some people might ask why we are interested in such kind of parameters. Okay, let's take a simple example. Imagine now you want to have some road trip. Of course not in this snow, but if you want to do so, what stuff do you think you might bring? I think nowadays the GPS is very necessary. However, the GPS data have to go through the atmosphere in order to reach to our receiver. And most of the time, the atmosphere is pretty quiet, so there's nothing to worry about it. But sometimes, if there is some irregularity happening there, then the data we received might be wrong, and even sometimes we might get lost of them. As a result, it is necessary and reasonable for us to have a better understanding of what is going on in the atmosphere. And the winds and the temperature are two of the most important parameters of the atmosphere. So the methods we're using here is by using a Febrile interferometer to observe the 630 nanometer red light emission in the atmosphere. I'll briefly talk about this topic. So the 630 nanometer red light emission is caused by some dissociated recombination of complicated chemistry reaction in the atmosphere. Anyhow, the emission intensity is showing in this plot as a function of altitude. The x-axis is intensity and the y-axis is altitude. It is clear that most of the intensity is concentrated in between 200 and 300 kilometers, with a peak at around 250 kilometers. And let's take a look at the Febrile interferometer. FPI is actually two parallel slabs, and assume there is coming light in this way with the incident angle theta, and then all of the parallel transmitted light can be focused to a point P on the screen by some lens. Of course, the position and the intensity of the point P depends on many factors, such as the incident angle theta, the thickness of the slabs, and so on. So if the incident angle theta changes, then the position and the intensity of the point P will change as well. As a result, we can get the phase pattern as shown in this plot. The x-axis is the phase changing, and the y-axis the intensity of the phase pattern. So how do we use such kind of phase pattern in order to get the temperature and wind velocity? It is actually not that hard. If looking at this phase pattern, so if the temperature is higher, actually the width of each cycle of the phase pattern will be larger as well. As a result, by measuring the width of the phase pattern here, we can know the temperature in the atmosphere, and we call that Doppler broadening. And as for the wind velocity, if there is some wind happening in the atmosphere, it will cause the phase pattern to be shifted. As shown in these two plots, we can see clearly that the first peak here is shifted to here in the second plot. So by measuring that shift, we can get the information of the wind velocity, and we call that Doppler effect. So in our model, by only one FPI, we assume there is some FPI placed on the ground, and with the looking direction in this way. Actually, each point in this line will produce some phase pattern, as I just showed, to the ground. And the phase pattern we finally got is actually the summation of all the phase pattern by each of these points along this line, and weighted by the air glow at that point. So by Doppler broadening and Doppler effect, we can get the information of a weighted average temperature and weighted average velocity, wind velocity along this line. But one thing we are not very happy about is because this value is only weighted average one. Most of the time, we are more interested if we can know exactly at what location the winds and the temperature are. As a result, we can introduce one more FPI and thinking about tomography reconstruction. In this plot, we assume there is two FPI placed on the ground, both of which observing the same amount of atmosphere, that is this region. Here, I only consider a two-dimension case, that is, I fix the latitude, and I assume that the region we are interested in is in this longitude and altitude plane. Of course, we can change in the observing direction. As a result, we can get many observations. And if we divided the longitude and altitude into many intervals, we can assume that inside each such kind of grid, the winds and the temperature is identical. Therefore, we can get the forward model for the air glow intensity as shown in this equation. The Q is our observation vector, the H is the weighting matrix, the A is the air glow profile, that is also what we want to reconstruct, and N is the noise. Same thing here for winds. So a very intuitive way to inverse this problem is by Fourier inverse. We do the singular value decomposition for the H matrix and Fourier inverse it and get the reconstructed one as shown here. But if we substitute this forward model equation into this equation, we can say the reconstruction one is actually the true value plus some noisy term. And if the sigma k here, which is the eigenvalue of the H matrix, is very small, it turns out that this term will be very large, and that will ruin things. Like showing here, the x-axis is the index, and the blue line shown here is the eigenvalue. Because we rearrange the eigenvalue in a decreasing way, so it gets smaller and smaller. And the green light here is the noisy term in accordance with each eigenvalue. We can see clearly when the index is larger and larger, the eigenvalue is smaller. As a result, the noise term is extremely large. Okay, so here is my one result. This one is the initial or original air glow profile. We can take a look at this profile, and the x-axis is the longitude, and the y-axis is the altitude. And each pixel here, the color shows the intensity of the air glow at this point, and air color bar is here. So this plot here is the reconstruction by the Fourier inverse. We can see it is very noisy, and we can hardly get anything useful from it. So to improve this problem, we apply the regularization. So regularization is assuming we have already know some prior knowledge of the reconstruction profile. Like showing here, this is just the L2 norm residue error that it shows the data fidelity. And these two terms, we call that penalty constraint, which is the priori knowledge. So let's go back to this plot. And since the air glow, we can say it is very smooth horizontally, but change a lot vertically. So we have to consider these two parts different. Here I have two terms for the penalty. The first term is for the horizontal direction. D1 is the first derivative gradient, and it aims at smoothing out things. And the second term is for the vertical direction. the A0 is some reference image, and D2 is second derivative gradient. So we aim at to preserve the peak in around 250 kilometers. And solution to this equation is given here. And we call that Tikhonov regularization. Another regularization I use here is total variation. So it is pretty much same as Tikhonov. The only difference is we use the L1 term here and here instead of L2 term in the Tikhonov. So total variation can much preserve the high frequency information as a large variation or the age information in an image. And the solution to this one is given here. Okay. Here, now I will talk about my simulation results. I simulated two situations. One is during a quiet time, and another situation is when there is some irregularity in the atmosphere. So in this first quiet time situation, I simulated three different kinds groups of observation, and geometry are shown here. In the first group, I simulated over 100 observations. So each pixel showing how many times that how many observations going through this region. And in group 1 and group 2, there are only 16 observations. And in group 2, most of the observations are only concentrating in this region. And group 1, they are more spread out, though they cannot cover every region. They still can spread out the whole region. And here is my simulation result, reconstruction results. At this time, assume the air glow profile has the noise with the standard deviation around 0.4, and A1 is our original profile. A2 is by group 1 reconstruction. A3 is by group 1, and A4 is by group 2. Actually, I think all of them are pretty good because the noise at this time is very small. And we do not include any irregularity at this time. And this reconstruction is for the wind when noise is around 5 meters per second. Still, I think all of them are pretty good. And this one is when noise is around 15 meters per second. So to my surprise, that this A2, that is with over 100 observations, is very noisy. So the thing I explained here is because the noise is larger. So it means when different observation observe same small region, it can get different results due to the different noise, and that will cause some conflict in the final result. And the A3 is the best among these three observations, and A4 is not good because remember, our observations are only concentrated in this region, so we do not get information in this region. So next, I simulated when the background wind is disturbed by some wave with a horizontal wavelength around 400 kilometers, like showing in this plot. And besides the Tikhonov and the total variation, I also consider two other kinds of regularization. So this one, I use the Laplace operator here instead of the first and the second derivative. And here, I use the weighted Laplace operator shown here, which can more capture the variation of a wave structure. And here is the result when noise is around 5 meters per second. A1 is by the Tikhonov, A2 is by total variation, A3 is by Laplace, and A4 is by weighted Laplace. We can see clearly that Tikhonov is the worst one among these four because it uses L2 norm, so it won't smooth out an image, so it will lose the larger variation of image. And this three can clearly capture the feature of a wave. And I personally think the weighted Laplace is the best because it not only shows the peaks of the wave, it can also show the gradual change of the wave in the structure. This is another result when the noise is around 15 meters per second, and I think it is pretty similar to the previous slide. Okay, so that is my talk. Thank you.
Time for questions. Do you have any question?
So you mentioned that you're interested in this because it would affect GPS transmission, right?
Yeah.
So is there any data, or I mean, can you comment on that, how it affects electromagnetic wave propagation, how wind speed could affect electromagnetic wave propagation? I mean, I kind of understand that if there are clouds or something, so then the propagation is different through them. But I don't understand how wind velocity could affect propagation of electromagnetic waves.
Okay, so I think because this is a little complicated. When you have large winds, it will propagate to the ionosphere, and at that region there are many ions and electrons there. So because of the wind and considering of the magnetic field of the Earth, it can cause the electron and ions to move in an irregular direction. As a result, when the signal from the satellite goes through them, it will be disturbed.
So it's more because of interaction in the, I mean, on Earth, wind speed wouldn't affect electromagnetic propagation, right? So you're saying that it's more because it's combined with the effect of ions or something to.
Yeah, it more related to can change the move of the, yeah, pretty much.
Other question? I have a question.
Okay.
So in your simulation, how have you determined the regularization parameters for the weight for Laplacian operators?
You mean like A1, A2 in the equation?
Yes. Is it determined from some physical model?
I basically use the air curve and GCV algorithm, but since I have do asking about the two parameters, how do I determine them? Or
so how do you find a good value for the regularization parameter?
okay, yeah, I basically use the air curve algorithm and GCV algorithm, but since I have two different regularization parameter here, so I found one of my parameter is easy to find because I fix one and change the other and can get where the corner of the air wave is and get that parameter. But another parameter is kind of little art to do so because I have to try and see the result in order to determine which one to choose.
So it has been tuned empirically from some observation, right?
Yeah, kind of.
Okay. Any other question?
So do you have enough data? So your system is underdetermined or overdetermined system for solving the linear inverse problem?
I'm not quite sure. Can you repeat your question?
So the question I'm asking is, so we are solving a linear inverse problem, right?
Yeah.
So the system is underdetermined or overdetermined. So do you have enough?
I think it's undetermined.
Underdetermined.
Yeah.
Okay.
Because I only have like 16 observations, and the pixel the number of pixels in each region is over 400. So basically, I can because the thing for FPI is because it needs almost 5 minutes to do one experiment. So I cannot do many observations because every 5 minutes actually the wave is moving. So if I do a lot of observation, actually the wave I observed later is not the original one. So I can only do a limited number of observations. So this is under determined.
That fits the framework of complexity.
Okay, thanks for the speaker again.